Thank you for the introduction. Good afternoon. My name is Hao Tian. I'm from Purdue University, and I would like to present our work unveiling the Mr. 4.5G performance in the wild. So we all like faster data speed, right? As I can recall that LTE was firstly launched in about 10 years ago. So, okay. Is it fine? Okay. Okay. So I think over this decade, we are seeing the evolution of radio access technology from 4G LTE to LTE-Advanced, LTE-Advanced Pro, and 5G New Radio. I think in the current stage that the 4.5G LTE-Advanced is the most common one that is widely deployed in the US. And we can see the efforts of mobile operators to keep upgrading their network infrastructure to support to improve their system capability. However, in sometimes we can still get slow data speed. You will feel really frustrated if you find that your mobile device can only achieve 2 MB. When in this case, you will see that your mobile device is limited by the raw network capability. We can achieve much better data performance. So here is an using AT&T network. So the experiment like this, we walk along a specific road to a target location. And when we reach the location, we start the first round of file downloading and found that our mobile device can only provide a 1.5 Mbps downloading speed. But the interesting thing is that if we reset our mobile network by turning on the airplane mode, by turning the airplane mode on and turn it off, and immediately we can achieve 15.9 downloading speed, Mbps downloading speed. So that means in the first round, about 10 times of data speed is missed. So we repeatedly run this experiment in many runs, and we found that this situation happens in multiple runs. So it's not a corner case. So what is happening here? If we check the RC message collected at device side, we can find that actually different serving cells are used to serve our mobile device in these 2 rounds of experiment. So here, in the first round, we found that our mobile device is served by 3 serving cells, P1, S1, and S2. While in the second round, another 3 different serving cells are used, P2, S3, and S4. So this technology is actually first used in LTE-Advanced. It's called carrier aggregation. So it allows our mobile device to use an aggregated carrier so we can take the benefit of wider radio bandwidth. So now we have the first finding, we have the finding 1, which is performance gap does exist in reality. So we found that what a mobile device actually gets in reality is not equal to what it could have got at best. And hence, we get the performance gap. So question 1 is, how common and how large is the gap in the wild? So to answer this question, we conduct a static case study at 14 typical locations in West Lafayette, including campus, suburban, and the rural area. So we run many runs of file downloading experiment at each location across different hours and different days. So we found that actually the data speed is largely depends on what serving cells are used by our mobile device. So here is an example at location S1 in suburban area. Actually, this is exactly the location we get the previous example as round 1 and round 2. And we can see at this location, our mobile device can actually served by 12 different serving cell sets. And the data, the downloading throughput is different when our mobile devices are using different serving cell sets. So one thing we have to admit is that our observation is only a lower bound of the real performance gap because it's still possible that we didn't observe the best or the worst serving cell in reality. So here is more AT&T instances at campus and the rural area. While compared with previous cases in suburban area, we can see that we have similar observation in campus, although that here the best serving cell set can provide faster speed, so we have larger performance gap. But in rural area, the performance gap is much smaller. So we found one important factor is that actually the cell density is varies at different locations. We can see at the C1 location, which is in campus, there are totally 9 different cells in 7 different serving cell sets. But in the rural area, we can only observe 3 different serving cells from 4 different serving cell sets. So how about other carriers? We extend our static case study to T-Mobile, Sprint, and Verizon, and we can see that Verizon here has very similar result to AT&T because they both make pretty dense deployment in West Lafayette area. While for T-Mobile and Sprint, we observe fewer serving cell sets and cells, and also we have a smaller performance gap. Well, the exception here is Sprint. We observe much higher speed in suburban areas, so also we get a pretty big performance gap. So now we have the finding too, is big performance gap is not rare. At least we found that it happens for all operators in the whole West Lafayette area. So the question too is, how is the performance gap at larger scale, for example, at city scale? So to answer this question, we run driving experiments. So the idea is we drive across every main road in West Lafayette area, and we drive from different directions. And we collect a big enough data set which covers 700 hours and 8,000 kilometers distance. So this is a figure which shows the count of serving cells of AT&T at each road. And we can see this actually do shows the efforts mobile operators put to make a dense cell deployment. So in order to quantify the performance gap, we use 2 simple metrics. So the idea is, given the file downloading samples we collected in a specific location, we identify the best and the worst serving cell using their medium throughput values. And these 2 metrics is delta, which is the absolute performance gap, and the gamma, which is the relative performance gap. The reason we need to use both is because, for example, here at location C5, we can, although the absolute performance gap is pretty small, but we can see the relative performance gap is big. The reason actually it indicates that the worst serving cell used in location C5 actually has very poor performance. So using these 2 metrics, we quantify the performance gap from our driving experiment and see that the gap actually is common and big. For example, here for AT&T, we use AT&T as an example, and you can see that at more than 20% of places, we can observe an absolute performance gap of 30 Mbps, and the relative performance gap is 7. Sprint, that the relative performance gap is pretty small. The reason is because actually Sprint can provide higher downloading speed, for example, over 100 Mbps, and that's why we can see the relative is small, but the absolute performance gap is still big. So now we have finding 3, which is performance gap is common and big at city scale. So the next question is, why does the mobile device miss the best or the good performance? So this measurement study has already shown that the network potential doesn't equal to the real data speed our mobile device can achieve. So we know that network operators are making heavy investments. They are trying to upgrade their network infrastructure from LTE to LTE-Advanced, and they are making denser cell deployment. For example, here we plot the CDF of the observed serving cells, including both P cell and secondary cell for all 4 operators. And we can see that such dense cell deployment actually means that all mobile devices will have more and more serving cell options to use. But the problem is the mobile device doesn't always select the best serving cell sets. So the question is, why are these good serving cells are missed? So there are 2 parts, right? The primary serving cell and the secondary serving cell. So we find that for primary serving cell, the selection of P cell is actually determined by cell selection and handover mechanism. And those are actually largely determined by radio signal strength as regulated by CGPP standard. For example, here I can show you a simple procedure of a handover. So we can see that the serving cell will send the configuration to the mobile device connected to it. And based on these configurations, the mobile device will make measurement of radio signal. And when some condition is satisfied, the mobile device will send the measurement report back to the serving cell. And based on this measurement report, the serving cell will make the handoff decision and ask the device to execute the handoff. So we can see here, radio signal measurement is the important part. But the problem is, cell with best radio signal doesn't mean that it can always provide us with the best data performance. And the next part is secondary cells. So we found that the selection of secondary cells are actually determined by P cells and follows operator-specific strategy. So here, what we're trying to do is we count the number of different secondary cells used by each P cell. So here we can see, although there are the left one is the absolute value, and the right one is the ratio, shows the ratio. And we can see that although we are given many cell options, but the secondary cell used by each P cell is really low, only 1 or 2 in median value. The problem is, so amongst all these surrounding cells, only very limited cells are considered by P cell to use as a secondary cells. So to sum them together, we have the finding 4, which is we believe that it's today's cell selection mechanism lead to the performance gap. So the question is, what's next? So actually, I think the key question is here, how can we achieve the full potential of the existing network capabilities? So I believe that our measurement study actually gives us 2 important implications here. So the first one is, if the application is throughput intensive, we should choose the serving cells more carefully. The reason is because we know there are some transient factors that can influence the network performance. For example, the radio signal strength, the radio signal quality, and also the traffic load, the cell load. But the thing is, based on our measurement result, we can see that the used serving cell is actually the persistent factor that can influence the data performance. And the second implementation here is that we found that the existing cell selection and handover mechanism, they are designed for mobility, and they focus on mobility, but they are not optimized for data performance. So put them together, we believe there is a promising approach which can somehow solve this problem, is if we can take some proactive device-side actions to change the serving cell we are used. And in that ways, we can improve our data performance. But as you can imagine, there are many practical challenges, and it's our ongoing work. So that's all my presentation. Thank you for your time.